Okay, guys, welcome back. We're going to be taking a look at 10.2 in statistics, day 2. And this is actually one of those, days that everyone looks forward to because this is when I get to feed you again. And unfortunately, I won't get to feed you with chocolate chip cookies because circumstances. So we're going to take a look, and I actually consumed a bunch of Chips Ahoy cookies myself. And let's see what we came up with. So this is saying, is there a difference in the number of chocolate chips in Chips Ahoy cookies versus the number of chocolate chips in Meyer brand cookies? Now, if you don't know Meyer brand, that is a Midwest generic brand associated with the Meyer's supermarket, really. If you ever get the time, ask me about my Myers story. There's a really fun one there. That's the only reason I know what Myers is. So each pair of students is going to count the number of chocolate chip cookies in one Chips Ahoy and one Myers Chipsters cookie. So we didn't use Myers. We used Ralph's brand Kroger Chipsmate. So we use Chipsmate. Due to factory process, we can assume that the population of the number of chips are approximately normal and the samples are random. So we're going to highlight that because that's going to be necessary for us. So we're going to say that the distribution of the number of chips are approximately normal and samples are random. Okay, so we don't have to worry about that. So here's what we're going to do. What I did is record the number of chocolate chip cookies in each cookie. So I went and dissected one Chips Ahoy cookie and I got 17 chocolate chips. And then I did the same thing for a Chipsmate, which is the Kroger brand. And I got 22 chips. So it seems as though the Chips Ahoy brand actually has less based on that one set of cookies. So next thing we should do is just go ahead and, let's make a sample because one cookie is not going to say a whole lot. What if we took a sample and looked at the mean of the sample? So from the experimental data that we did last year, and I went ahead and I added mine to it, we had the Chips Ahoy with those numbers of chips, 17, 19, 21, 16. You can read those yourself. Chipsmate had 22, 20, 14, etc., etc. I went and I did the dot plots because I'm extra like that. Didn't need to do the dot plots because already we're told that the samples are approximately normal, or the samples are going to come from an approximately normal distribution. Next, let's find the mean numbers. So I took those Chips Ahoy and Chipsmate data, I stuck them in my calculator, and I came up with an X bar for Chips Ahoy. That was 18.4 with a standard deviation of 1.78. And then I did the same thing for Chipsmate, and I got 19.4 with a standard deviation of 3.6. You can tell the difference in chips between Chips Ahoy and Chipsmate was -1. So if we repeated this process many times and created a dot plot, we would have, that would be a dot plot of the differences. We would have a sampling distribution for X bar 1 minus X bar 2. What would the shape, center, and spread be? Well, the shape is going to be approximately normal since those populations are also normal. The center is going to be the mean of Chips Ahoy minus the mean of Chipsmate. And the spread, the variability, that's going to be, there is this formula right here. It's going to be sigma of Chips Ahoy squared over the number of Chips Ahoy cookies plus the sigma of chipsmate cookies squared divided by the number of chipsmate cookies. Now, you should also remember that those numbers, if we knew the mean, then we would know the standard deviations. So we're going to approximate those standard deviations with S, which is the standard deviations of our sample. That means that we have to use a t distribution. So, have the conditions for constructing an interval been met? Well, if you remember, most of those conditions were met. We were told that we had approximately normal distributions, and we had samples that were from a random distribution, or from a normal distribution. So yes, we have a random distribution because the samples are random, and then normality comes from our question number 3. I don't want to rewrite that. And what about that 10% rule? Well, our samples were 10 each, so are there more than 100 Chips Ahoy cookies out there? I've eaten more than 100 Chips Ahoy cookies myself. What about Chipsmate? Well, I haven't eaten 100 Chipsmate cookies, but just looking at the shelves on Ralph's, I can tell you there are more than 100 cookies out there. It only takes 2 or 3 sleeves. So next, we're going to construct that 95% confidence interval for the mean difference, or the mean of the true difference in the number of Chips Ahoy cookies. Now, you already know how to do this, so I feel pretty comfortable just going to the answer here. It's the generic formula, the general formula, which is the point estimate plus or minus our margin of error. Specifically, we're going to have X bar of Chips Ahoy minus X bar of Chipsmate plus or minus T star. There's that T star because we're using S instead of sigma. Multiplied by the square root of those two variances added together. Substitute the numbers and then show the answer. Our answer is -1 plus or minus 2.9. Check the math. Make sure I didn't do something wrong. You never know. Next, do we have evidence that there is a difference in the average number of chocolate chip cookies in a Chips Ahoy and a Myers Chipsters? No, we're actually using a Kroger Chipsmate. So is there an actual difference? Well, I don't know. I mean, I calculated in point estimate plus or minus margin of error. What if I actually bore out that mathematics with the addition and subtraction? Well, what would I get? Oh. Well, here we go. We're 95% confident that the interval from -3.9 to +1.9, that's -1 minus 2.9 and -1 plus 2.9. Well, that interval contains the true value of the mean difference in chips. So what does that mean? Well, the interval contains 0, so we can't conclude that there's a difference in the average number of chips. We can't actually conclude, based on our samples, that one brand has more chips than the other. So can I generalize that for you? Yeah, we can generalize. If the entire interval is negative, that means our parameter from population 2 must be greater than our parameter from population 1. Likewise, if both of our A and B are positive, then we can tell that, or we can conclude that the parameter from population 1 is greater than the parameter from population 2. But if the interval is like our interval, where the lower bound is negative and the upper bound is positive, we can't tell. Maybe pop 1 is greater than pop 2. Maybe the parameter from population 2 is greater than the parameter from population 1. And maybe, just maybe, the two parameters from population 1 and population 2 are equal to each other. So we don't know. Possibly they have the same number of chips. Having done that, it's time for us to take a look at our important ideas. Let's scroll down and take a look at those. Okay, so learning target 1. Those two the shape is approximately normal if the 3 conditions hold. Randomness, 10%, and of course our friend Fluffy. No, that's not right. That should be normal, which includes Fluffy. Oh, well, no, Fluffy is all. That's normality condition. Remember, Fluffy comes from the dog, Hagrid's dog in Harry Potter. I like it. If you don't like Harry Potter, then you can choose whatever you want to call it. Center of this sampling distribution, that's going to be mu1 minus mu2, which can be estimated by x bar 1 minus x bar 2. What about variability? Well, you can see we have this addition of the two variances put together, and that's going to be approximated with S1 squared over N1 plus S2 squared over N2. Now, those approximates are the only thing that we're going to have if we're actually doing statistics. We're not going to know mu. We're not going to know sigma. We have to estimate that based on x bar 1, x bar 2, S1, and S2. What about the changes in the 4-part plan for a T interval? Well, there's not a whole lot of changes. The first change would be the name. Of course, the name is going to be a 2-sample T interval for mu1 minus mu2. Conditions, that's the same conditions that we had from the previous box, random 10% and, normality or Fluffy. The specific formula, I think you see that, x bar 1 minus x bar 2, plus or minus t star, and then the variance is added together. And then degrees of freedom. Now, this is the one that is massively different. What we're going to use in this class is called the conservative degrees of freedom. Now, there's a long formula that you can use to find degrees of freedom, but we're just going to use this simple formula, and that is you take the smallest sample size, you subtract 1, and that is your degrees of freedom. Now, on the AP test, they're going to recognize and grade completely anything that has a conservative estimate. If it has that crazy formula from your book, it'll mark that correct as well. And there are a couple of other ones that they're going to mark correct as well. But, for my money, the conservative one is the easiest, so that's what we're going to use. Let's check our understandings. Mr. Wilcox's classes performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rate. 20 students in class volunteered to take part in the experiment. All of the students measured their initial pulse rate in beats per minute. Then Mr. Wilcox randomly assigned the students into 2 groups of 10. Each student in the first group drank 10 ounces of cola with caffeine. The students in the second group drank 12 ounces of caffeine-free cola. And then all students measured their pulse rates again. The table below displays the change in pulse rate for the students in both groups. So we got those. I would recommend you put those in your calculator right now. Verify the mean and then also calculate standard deviations, because you're going to construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate. So, first of all, pause it right here and figure out the state part of the state plan, do, and conclude, the 4-part plan. Okay, I think you can see that mu1 minus mu2 is the true difference in the mean change in pulse rate, caffeine minus no caffeine. Now, I think it's important for us to note that we are defining the difference. We're not defining what 1 and 2 is, so our test is really about the difference in means, not necessarily about population 1 and population 2. So that brings us to part 2, which would be our plan. What is the plan? Okay, so for plan, we had a 2-sample t-interval from mu1 minus mu2. We're told that it's randomly assigned from a quote. 10, both samples are size 10, so 10 times n is 100 for both samples. So I assume, no, I don't have to assume, I know there are more than 100 caffeine drinkers, and I also know that there's more than 100 non-caffeine drinkers. I went and did a dot plot of both samples, didn't take that long. And I found that neither sample showed strong skew nor outliers. So the next part for us here now is going to be for us to get a, what is that? State plan do. We need to do. Remember, do consists of, number 1, your general formula, number 2, your specific formula, number 3, your work, and number 4, your answers. So pause it here and get to that. Okay, here we got our general formula, PE plus MOE. Our specific formula, that's from above. Substitute our numbers, 3.2 and 3.2 and 2.0 for those means. 2.7 and 2.62 are the standard deviations, and you come out with 1.2 plus or minus 2.69. Okay, last part is you're going to be your conclude. Let me help you out by starting off with, or giving you your set phrase. All right, there's your set phrase. Go to town, start filling in the blanks, and pause it here, and we'll come back and check. And here is the thrilling conclusion. We're 95% confident that the interval from negative 1.49 to 3.89 captures the true value of the difference in mean change in pulse rate, caffeine minus no caffeine. So that's it, everyone. Your 10.2 day 2, all about your confidence interval for a difference in means. 2 samples this time. All right, have a good day. See you next time.